with the years. Welcome. I'm really happy today to have one of our own faculty giving the colloquium. But first, let me just point out next week's colloquium is by Eric Drew from Florida International University, who is talking on engaging students in modeling instruction. This week's colloquium speaker is our very own Professor Haeffner. So Professor Haeffner did his studies, and he started his research in high precision AMO work at the University of Mainz. And for his graduate work, he worked on high precision measurements of the electron magnetic moment. He had a number of research positions following that, including a very prestigious Marie Curie Fellowship from the European Union. Before coming to Berkeley in 2009 as an assistant professor. He, since coming to Berkeley, he has been awarded the Sloan Fellowship, the NSF Career Award, and the Dr. Young Investigator Award. So he's had a very good start at his career here at Berkeley. So today he's going to be talking about information, decoherence-free subspaces, and Michelson Morley tests with electrons. So let's welcome Professor Haeffner. Yes.
Yeah.
Yes, thank you very much, Steve, for the nice introduction, and thank you all for coming. I hope I made the journey worthwhile. As Steve, let me whether we can see this on. Okay, so I will talk about quantum information, decoherence-free subspaces, and the Michelson Morley test with electrons. Probably most of you don't really know what all these words are connected to each other, but I hope during the talk this will become really clear. For my talk, I will give you first an introduction into quantum information. I start very fundamental, and then we'll go on more into how we want to do quantum information processing with ions. And one of the hurdles in doing so I will discuss here, and that is improving ion traps in order to perform quantum computing. And then I will talk about the application of the tools we've developed here, a Michelson Morley test with electrons. So, quantum information. Quantum information is a merger of physics and computer science, so to speak, and therefore I want to start with basically discussing a little bit how physics and information are related. So in physics, we are often interested in describing a rather complex or complex phenomena, sometimes spectacular. And the way we do this is we extract the situation, extracting some relevant information, or we hope it's relevant, or maybe the full information. We might necessarily don't know that. Then we perform an algorithm, we get some new set of information, and then we just take it for granted that this new set of information has something to do with reality. So what we are doing there is we basically going back and forth between information, and many of us maybe hope that nothing will go wrong in doing so. So there seems to be a quite close relationship between physics and information. And Wolf Landauer actually went one step further and made this claim that information is actually physical. So what can he mean with that? So what he actually means is that if you talk about information, you actually have to think of information being physically implemented, if not run. That was at least his view. It's not completely undisputed, but the way he arrived at that conclusion is by looking at Maxwell's little thought experiment about the demon. Basically, the demon has a little door. He can move open and close without actually performing work. The door separates two containers of gas, which are initially at thermal equilibrium. And then what the demon does, he looks at the gas molecules, the individual gas molecules, and then, for instance, the fast one arrives, he opens the door, and if the slow one comes, he closes the door. We all know what happens after some time. You will have a cold gas here or hot gas there, and it seems that you have actually done work. So what's going on? How can you basically get rid of the entropy? And when you look closely at this, what's actually happening is that the daemon has to look at those molecules. The daemon actually acquires information. And so the daemon has to store that information somehow or forgets the information. If the daemon forgets the information, that's Landauer's principle. Landauer claims if somebody forgets the information, you actually necessarily generate entropy. So that's Landauer's principle, clarifying, basically making the statement that you have to consider the physical aspect of information. So if you accept that information is physical, then it's a short step towards saying, oh, well, information you should actually treat as quantum mechanics. So you want to generalize the concept of information, assuming that information can have also quantum mechanical aspects. The simplest way what distinguishes that is by thinking in terms of what a bit or what a quantum version of a bit might look like, determine a qubit. And a qubit you can think, for those who are familiar with nuclear magnetic resonance, for instance, as a spin pointing either up, parallel to the magnetic field, or down, and of course, arbitrary angles, superpositions. Or if you're an atomic physicist, you might think of an electron being either in a ground state or an excited state, or any superposition there. So far, this kind of physics is just the physics of a two-level system, and we call this the fundamental information area in quantum information. The power of this, why this actually gets interesting, is when you start to combine. So here I have written the quantum state of a 3-qubit register. So I have 3 qubits, they can be in arbitrary states, and I have to use already 8 complex numbers in order to represent that state. Where this leads to, I'd like to illustrate here. Here I have the number of bits. I choose examples, for instance, classical versions. And on the right side, I write some random qubit register, how I would have the parameters. You can see for 8 qubits, there's a big distinction how many numbers I need to write down. And if you basically play this game to the end, and the end is actually at 300 qubits, so to speak, because if you have 300 qubits, you would need as many atoms as they are in the universe in order to encode this 300 qubits. So this gets a little bit ridiculous. And this leads then to the ideas that you can use these quantum bit registers to solve, for instance, the Schrödinger equation of 300 interaction states. If you want to do that in the most general case, meaning that there are no simplifications possible for whatever reasons, maybe somebody was really nasty and gave you a very complicated interaction, you cannot do it because you would need as many bits in a classical computer as there are atoms in the universe. It's not very practical. So the idea is instead to take 300 quantum bits and engineer the interaction which is given to you, and then basically read in the end the result of the system, and that's called quantum simulation. And that's one of the big fields in quantum information at the moment, where people hope to actually outperform classical computers in some cases. So quantum computers can solve, and I emphasize certain tasks because they are actually, to be honest, not too many, but they can be much more efficiently than classical computers. It's actually more interesting than that. You cannot only cheat it here a little bit, we simulate a particular system with a very closely related implementation, but it's more interesting if you go to the mathematical realm and actually you can implement quantum algorithms where you can factor large integers where there is no known classical algorithm which does that efficiently, and that's basically what kicked off the field in 1995. Also the search of an unsorted database. All these applications, this is really driving the funding at the moment, are very advanced. They will require many thousands of qubits, and I must admit that we are not there yet, but maybe 10, 20, 30, maybe 100 years. I don't want to accept this. So, but for the researchers in the field, I think the motivation is different. Many of us are interested actually in understanding quantum mechanics. So we like to play with quantum mechanical systems to understand better how they work. Also, the field has started to impact seriously condensed matter physics, helping to classify quantum phase transitions, for instance, also in chemistry and biology. For instance, in biology, people think about how can the photosynthesis so efficient at transferring like energy from a reaction center to actually where it wants to be, and there are people who claim that actually entanglement is responsible and the tools for quantum information are very suited to actually study this phenomenon and actually find out whether this is really true, whether you need quantum effects. From Raphael Russo, we also learned that it has impact on cosmology, the physics of black holes. It's important whether there's unitary evolution or not in order to unify quantum gravity with talk about quantum gravity in the first place. Maybe. I'm not so familiar with that, but that's my impression I get. And hopefully there are unforeseen applications. We'll see later on. Okay, so we are working with +1. This is how an quantum computer might be envisioned. We have electrodes here in yellow, and we apply certain voltages to them, and the idea is to store a bunch of ions on top of this surface. And each of those ions is supposed to represent a qubit, and we have to manipulate these qubits. These qubits are floating in vacuum, so they're very well isolated, and that's what we need in order to have long coherence and really to have quantum mechanical properties. So how can we talk to them? One way is to shine in laser light. So I have a laser beam here, hitting these ions, and those ions start fluorescing. They can switch off the laser beam, switching off the put their lens, and then image this light onto a CCD camera, and then we can obtain an image as shown. So this will be, as you will see later, the readout, but we can also manipulate the internal degrees of freedom, meaning promote the electron from a ground state to another excited state with a different laser, here shown in red, and that we will see in a moment will lead to what we call single qubit operations. So let's look at a particular system. So this is the hardware. You can see here an ion trap here, about maybe 50 meters from here. In vacuum, it's a chip. You can sort of see the electrode structure there. And on top of this chip, we have, for instance, 3 calcium ions. They arrange nicely in this arrangement because the confinement in this direction is much stronger than in this direction. We put on propulsion to make sure that they don't sit on top of each other. And you can see they are nicely resolved, and that means that I can also walk with a laser to them immediately. Each of those qubits, or these calcium ions, can serve as a qubit. This is a simplified level scheme, so all you need to know for this talk, approximate the complicated calcium ion with these 3 levels. You have S1/2 ground state, a P1/2 excited state, and I can scatter photons from this by shining this laser frequency. And these photons are actually the photoeffective photons here. On top of that, and that's important, I have a third level, the E5 level. There's a delta L equals 2 transition, so that is long-lived. It's for about a second. And that will allow us to store quantum information in superpositions of the S1/2 and the E5. So let's see at the requirements. So we want to do quantum information processing. What do we need? It's fairly straightforward if we start from what a classical computer is. A classical computer first starts by erasing the register, or starting with a very defined state. And then basically what I need are 2 qubit gates, in particular the NAND gate, and I can complement what I want to get with the NOT gate. And then I work in some computation space, and I read out the result. So these are kind of the requirements we need to fulfill in order to. For quantum computer, it's very similar. We need to think how we initialize our quantum register, how we reset our qubits. And it turns out in order to perform an arbitrary algorithm or an arbitrary unitary operation on my quantum register, I need 2 sets of operations, single qubit operations and 2 qubit operations. Single qubit operations I just talked to an individual ion. 2 qubit operations I need to somehow have a state-dependent interaction between the 2 ions. Z+Z interaction for the specialist or whatever. And then I work, of course, instead of a classical computational space, I work in this 2 to the n dimensional pivot space, where n is the number of qubits, and you can see 2 to the 300 is a really big number. That's what I mean that we're talking about the number of atoms. And in the end, I'm going to need to read out to gain actually classical information because humans cannot really process it. So I want to go through the basic steps for a single ion to give you a flavor of what we are doing daily in our lab. So the first, our experiment starts with an initialization of the quantum state. Here's this reduced level scheme of calcium 40 plus actually. We have an S1/2 ground state, a P state, and a P state. Initially, we have an arbitrary superposition of the ion in the S and the T state. That's our qubit state, and we don't know whether we are here or here. We need to reset the system. It's fairly easy. I shine in laser light on this transition. The ion gets promoted to this level. It might drop down here, and then basically we are here, or it might fall back down, in which case I just repeat the excitation process till it actually drops down here, and this way I can initialize the system. You can also see that this process generates heat or entropy because that photon is spontaneously emitted into a direction I don't really know. And that's essentially this idea that we have to generate heat if we reset. And this is a single atom, so this is not a complex transistor. This is just a single atom. You can see how this happens. Next thing, I need to do a quantum state manipulation. This is the unitary operation, or the form actually the algorithm. And it's a laser pulse on this transition, S1/2 P5 transition. It's forbidden, but with enough laser power, you can drive it. So we do this, and this will actually represent our algorithm. And in the end, we need to read it out. And that's basically where you might think, oh, that's difficult to read out a single ion. So I'm going to show you that there's actually fairly straightforward. All we do is we shine a light on this transition, and either we see fluorescence, so we decide to here, it falls down here, up, down, and we get tons of photons, 10 to the 8 photons per second. So that allows us to take a CCD image. This is a 10 millisecond exposure time, and you can see, okay, there's a bright dot. The ion has been projected to this. Or it might have been projected to this state here, in which case the blue laser doesn't do anything. The ion remains dark, and I obtain such a CCD. This works, of course, also by multiple ions. Here I have 2 ions very close to each other, but you still can see that they're very separated. They're both ions are fluorescing. One ion is fluorescing, one is dark, the way around. So it's fairly easy to distinguish this. Those are experiments with single individual quantum systems, so we need to gather statistics. A single experiment won't tell us anything, not a lot. So we repeat those experiments with a rate of roughly 50 experiments per second, and on the order of 100 to 200 times. So we are ready for our first experiment, and these are Rabi oscillations. So what we do is we initialize first the ion in the S state, and then we record as a function of how long we keep that laser on the excitation probability. So this you can really read of 100 experiments in 50 times. I've got a dark ion 50 times of that bright ion, and that's what we put in. And if we have this interaction on for 200 nanoseconds or so in this case, you can see that with 50-50, I am in the ground state and excited state, so I've compared the superposition state S plus. If I leave the laser on a little bit longer, I completely flip the bit, so that's kind of a NOT gate. Whereas this is interesting that this here is what we call the square root of NOT gate, because square root of NOT times square root of NOT is NOT. It's just half a NOT. And with quantum information, if you're more familiar with nuclear magnetic resonance, you might also look at this vector here, which is essentially how the two-level spin goes from the south pole to the north pole, and then continues to rotate it. Keep that interaction on. Okay, with this introduction, I want to now get a little bit more specific and talk about what we are doing here. So our group is interested in making quantum information processing with flat-line reality. For this, we develop novel quantum information processing architectures. In particular, we are interested in hybrid quantum systems, meaning that we want to use dose conjunction or solid state approaches want to marry them with our very good quantum memory capabilities of the ions. We also have a project going on where we are mainly interested in overcoming some of the difficulties of pure ion-trap quantum computing, and I'll talk about this in a little bit more detail, so improving ion traps. However, then, so this feeds all and makes maybe quantum information processes in reality, but we want to use those tools also to do actual physics. So one is, of course, one big thing is quantum many-body physics, studying how quantum correlations, for instance, in this 37 ions propagate. I won't talk about this today. Rather, I want to talk about the application to fundamental physics, in particular fundamental symmetry. I will talk about these two topics. Okay, first, improve traps for quantum computing. So first, I need to state where the problem is. And I start by stating where the problem not is. So here we have our ions, and they are trapped here, and we have a qubit. And what is important in order to get a unitary evolution, or in order to be able to have quantum computation, is that we need to have coherence of this quantum state. This coherence is typically tested by what we call a Lorentz experiment, meaning you do a pi over 2 pulse and another pi over 2 pulse. On the top scale, you might think about going halfway up, then waiting for some time, and then if decoherence takes place, this block vector will shrink actually. But if coherence doesn't break down, and then you are able to fulfill the rotational unneeded rotation. Here's an experiment from 1991 with trapped ions from the NIST group, and they have done such a Lorentz experiment where the 2 pi over 2 pulse were separated by 9 minutes. 9 minutes means you probably can go to Gallis, get a coffee if the line is not too long, and come back in time to finish your experiment. And at the end, you might find your ion qubit is still alive, meaning that you have still coherence. So that's really fantastic. So that's not where the problem is. Here's where the problem comes in. We want to have also the ions talk to each other. We need that the ions, that we can have like a state dependent, so that the time evolution of one spin depends on the state of another spin. For this, if you want to do that in a scalable way, you need to bring the ions close to each other, and you also need to be able to separate. What that means is you need somehow to form these kind of potentials, and this goes, of course, is much easier if your electrodes, which basically shape those potentials, are close to the ions. That means we don't want traps where the ions are very far away from the electrodes. We want them close to electrodes. And then, of course, decoherence might be. It does not kick in actually on this level for the single qubits. It kicks in if we actually want those ions to talk to. And the way, so the typical distances we actually are aiming at are 30 to 100 micrometers. So that's when things seem to be able to. So the way we want to have them talk to each other is that we need to cool the ions into their motional ground state. So we take ions and we cool them such that they're in a motional ground state. The coldest temperature which is possible in the system. And what we need then so that we can talk to another ion is that they stay there. However, you can imagine if you're 30 micron to a surface, that might not be true. There might be, for instance, electrical field nodes hitting your ion to a first excited state. So people have measured this. So this is as a function of the waiting time, how long the ion was left in the dark, the probability that you have acquired one motion quantum. And you can see after 50 milliseconds or so, you have about a chance of 10% of being end up in an excited state. That means that your quantum gate will have only, after this, if you're running a quantum algorithm 50 milliseconds, that your fidelity is limited to 90%. And so people therefore put a lot of effort in characterizing this, what we call the heating rate of ion traps. They measure how fast these ions heat up. And they've done so as a function of how far the ion is from the electric distance. So this, what you can see is the closer you come, the more noise there is, and that's kind of what it's expected. The important thing, or the interesting thing maybe for you to realize that each of those data points is probably a PhD thesis. So it's kind of a tedious business. So you set up a vacuum chamber, you get all the lasers ready, you do your measurements, and then you're so anyway, so the problem or the interesting the thing relevant for us here is that this is where we should be. Actually, we should be below there. So, and it's not clear where this is coming from, why basically everybody gets higher heating rates than expected. What is important in our context here is this is where we want to be below this, because if we get our heating rates below this here, we can hope to implement what we call fault-tolerant quantum computing, meaning that we can implement algorithms which actually correct for quantum for decoherence, and in some sense you can make this way if you will live forever. So that's basically the goal, to go below this line. Actually, so this line is somewhat fuzzy, depends on how you want to do it, but that's a good line. So what's going on? How can we go from here to down? So yeah, motivated already. So we need really to know what is going on there, not only from a physics point of view, also if you want to make quantum computing happening. And also there are other technologies which have similar problems. For instance, I talked to Alex Sushkov, who is interested in measuring Casimir forces. He suffers from this noise. People who want to test how electrons and positons fall. Also, if you want to test general relativity and send a satellite up there, the gyroscope has actually problems which are very closely related. So you want to study what is going on. There have been a couple of suggestions, most notably Dave Wineland from this to evaluate these things first. He thought that's maybe patches on the surface. So you have your old surface, and then you have grains, and those grains have different crystal orientations, and then maybe grain boundary. We came up with another suggestion after talking actually to Mike Romy that there might be contaminants on the surface, something the atomic physics community has highly ignored, and that those contaminants have actually maybe dipole moments, and this dipole moment might be thermally activated, and we came up with an estimation actually sort of seemed to fit. And the Harvard group actually made an improved model of this. They basically really did a calculation of absorbance, for instance, neon on gold, trying to estimate how much noise they would get from this. And then they made really a microscopic model and predictions on fluctuating strength of particles. So it seems that what's going on has something to do with the surface. So what we did is we started setting up an apparatus which combines surface science fields with our ion trap capabilities to study this. So we trap a bunch of ions on here, and we measure the heating rate. We're able to rotate this apparatus facing down, and then we have kindly from Mike Romy loaned us a Auger unit where we can actually then look what is on the surface. So we shoot electrons onto the surface, and then from these fast electrons, Auger electrons are generated, and we measure the energy of those Auger electrons, then we can say which elements come from them. So that's what we did. So this is a pure gold surface, and not actually not gold, it's copper, aluminum. So you can see there's a nice peak of carbon and a nice peak of oxygen, no sign of oil. So then we did some treatment by shooting argon ions onto the surface with 300 eV energy, and then suddenly we see this at low energies, which is characteristic of metals. And if you look closely, the carbon peak is almost entirely gone, and the oxygen peak is also not gone. So we clearly have done something to the surface, and the question now is, has that anything to do with our heat? So this is a measurement. This is the heating rate. That's a function of the oscillation frequency of the ions in potential. This is before the treatment, and after the treatment, you can see that the heating rates drop by 2 orders of magnitude. So that means that in this graph, we were limited to heat by some surface effects, and at the moment we're trying to understand what these effects really are, because you can see some interesting structures in frequency space. We don't know where this comes from. We also want to mention that we come close to the Johnson noise limit in our setup, maybe a factor of 10, or maybe even less than a factor of 10 to the Johnson. So where does this put us in a global perspective? So this is a plot I showed before. The NIST group has done a very similar experiment where they cleaned their traps. They obtained also 2 orders of magnitude increase. Our starting point was a little bit better. We started here with the noise. And in our work, we reduced the heating rates also by 2 orders of magnitude and breaking through this following threshold for the first time in room temperature trap in a scalable system. The time electrode distance is really reasonable in order to perform quantum. Okay, so this might make all these applications possible, especially building an Eintracht quantum computer, and our collaborators actually in Innsbruck are gearing up at the moment, and actually they factored recently 50, but they want to, of course, factor larger numbers. So I want to come back to our motivations, what we want to do here. And in particular, I want to talk now about unforeseen applications. That's basically relates to the second 2 items on my title. So I want to take advantage of quantum information tools to look for unforeseen applications. And this unforeseen application was actually a Michelson test with electrons. So it came really out of the blue. January 2014, I said in the seminar. Anyway, so this is about the Michelson experiment. So first, I want to talk about what the Michelson experiment was, to give you some background. Probably all of you remember that. What you set up is you have a light source, and then you send a beam, you let it bounce back and forth after passing through a beam splitter, where it also bounces back and forth. In the end, you recombine it, and you look for interference. And the idea is that as the Earth rotates, or as this apparatus rotates, you can test whether the speed of light is isotropic, meaning that the speed of light in this direction is really not different from this. So if it would be different, if I would rotate the experiment, of course, I would see shifts in interference filters, and what you can see, or what you all know, is that Michelson Morley didn't see it. But I also want to point out that it's really only the isotropy. It's nothing about Lorentz. What's also interesting to notice, this experiment was in 1887, so there were no lasers around, so they actually use normal light, for instance, a sodium lamp. And they actually didn't look for interference filters, they looked for a color change. So essentially, when you use white light, you can see here when you observe this interference here, you can see that different light colors have different interference constraints, and then if the arm length change is actually a color you observe here. So different experiment than what many of us have. So this was the first test of Lorentz symmetry, and modern Lorentz, but there are many more tests now of Lorentz. For instance, accelerators like that at CERN wouldn't work if we would take Lorentz symmetry into account, and actually you can show that you can test Lorentz symmetry to about 10 to the minus 15 if you're using these accelerators. And then, of course, the classical Michelson Morley test, which will be most relevant to this talk. The modern ones are essentially you take the slab, you put the holes into it, you put mirrors at the end, and then you obtain 2 orthogonal cavities. Or you have an asymmetric cavity to test for Lorentz boosts. You can do also spectroscopy, and I will talk a little bit also about this. Those are so-called sliver experiments. And the recent one is one by Mike Hohense from the Müller group, where they actually check for Lorentz invariance of electrons. Or you look for astrophysical observations, like a modification of synchrotron radiation from high energetic electrons, for instance. and you can obtain some bounds there that the speed of light is the same for electrons and light. This is for the classical Michelson Morley experiment, how the accuracy has improved over time. This is really the idea. I test Lorentz symmetry for light, which presumably is the most effective candidate. The sensitivity as a function of time. And you can see that Michelson Morley already were pretty precise with roughly 10 to the minus 9. But people improved it, and recently they obtained a few parts of 10 to the minus 7. So that's how do these experiments look like? I already indicated that. Two orthogonal cavities. I lock two lasers through these cavities, the feedback, and then I beat these two lasers, and I measure the difference between the beat, and then I record that beat as I rotate this device on a table, and if I can see modulation of the beat frequency, I know that Lorentz invariance doesn't. Of course, nobody saw ever something. What we are here want to do here is that we want to do a similar test with electrons. For instance, you want to know whether the maximum attainable speed of electrons is c or not c. Or that's what we do here, is we want to see whether the energy of an electron depends on which direction it moves. So consider two electrons, they're moving at the same speed, they have different kinetic energy, they have the same space versus that. You could think of it as an anisotropic mass, or that space is contractible. Of course, I want to mention that also many other tests with neutrons and protons have parity. So how do you do such a Michelson Morley experiment with electrons? This is really the idea in this experiment. I want to check, is this energy the same as this? So how does it happen for light? You look essentially for standing waves in a Michelson interferometer. So I have a standing wave here, and a standing wave here, and then I look for the phase difference over here on this. So our idea was we need to get standing waves. Where do I get the standing waves from? Well, you open the textbook, you might come across this table here, the hydrogen wave functions, and those are the wave functions of electrons trapped in, for instance, hydrogen, and those are standing waves of electrons. And those standing waves, they have different orientations. So the idea is to put a nucleus here and to look for standing waves of electrons. How do we do this in our ions? We have here the Zeeman splitting of the D state. In the S state, this experiment clearly would work because the S state function is perfectly symmetric. The D state is not symmetric, has an anisotropic momentum distribution. Electrons move, for instance, faster for a particular Zeeman state in this direction versus this direction. So what we are looking at is looking at states where, for instance, the NJ projection is 5½ or 1½ and in this state, most of the momentum is in the vertical direction versus here the most of the momentum is in the horizontal direction. This comes really from the fact that here the wave function is much narrower in this direction in the Heisenberg uncertainty relation, which tells you that momentum uncertainty must be big. So the idea of the experiment is pretty simple. I generate a superposition of electrons moving in this direction, or having high momentum in this direction versus here, in the orthogonal directions, and then I assume maybe there's a preferred frame of reference. Maybe there's not, but maybe there is. Then this wave function is defined with respect to a magnetic field we apply, and that remains constant with respect to the Earth's surface. And as the Earth rotates, I rotate the direction of that magnetic field in this preferred coordinate system, and that means that I rotate the wave function itself. And if there's a Lorentz violation, it should show up as an energy modulation while the Earth rotates. That's the idea of it. So let's try to implement that. Start with our ions in a well-defined state. Then I apply what we call a pi/2 pulse on this transition, creating a superposition of the S and the E state, a single qubit gate, so to speak. the square root of naught. And then I apply a NOT gate on this transition, moving this part of the superposition up to the excited state, and this is how we can generate the superposition state. So that would be our starting. To recreate this state, there's a problem. The problem is that we necessarily have a Seemann effect because the angular momentum, we need to have an angular momentum. The angular momentum has, of course, a magnetic moment. The magnetic moment interacts with magnetic field, and our magnetic field won't be constant for sure. What that means is that the phase evolution will be affected by that magnetic field too, and we need to hold our magnetic field really extremely stable and need to make sure that nothing goes wrong. So what's resolution? Resolution is Decoherence-free subspaces. So the idea is to take two ions. And suppose I generate this state. The first ion has a projection of -1/2, and the second ion of +1/2. And then, so those are two ions, and then I superpose that with a state where one ion is really polarized downwards and the other one upwards. But you can see here, if you add those magnetic quantum numbers, they add up to 0, they add up also to 0. In other words, the effective magnetic moment of this part of the superposition is 0, and the effective magnetic moment of this part of the superposition is 0. What that means, if I change the magnetic field, the relative energy of the two states is not changed. But the momentum distribution is, so the momentum actually goes, is squared. So that means that the directionality of the momentum distribution is not really changed. And that means that this effect actually doubles. So I have now here, if there is a hypothetical Lorentz variation, I get Lorentz violation, I get twice the signal out of this. So this is illustrated here how this trick actually helps. On the top, you can see interference fringes, how they decay as I increase the separation time between the lensing lines. You can see that after 100 milliseconds, we essentially lost our coherence. So this is for eye number 2. For eye number 1, you can see this also. You don't see the interference fringe because you have coherence. However, if you look for correlated excitations, you can see the interference fringes happily go on. And it has been shown that this can actually improve the coherence time by a factor of 10 to the 4. That's why it's called a decoherence-free subspace, because you exploit symmetry of the noise, or symmetry of the quantum state to reflect a certain kind. We use this technique in the simplified version. So here's what we do. We first perform laser pooling on the two ion crystals. We apply a pi/2 pulse, this effective pi/2 pulse on the left ion. Then on the second ion, then we're going to wait 100 milliseconds, and then we apply the inverse unitary operation with a pi pulse and then a pi/2 pulse. You remember those were the two different transitions, and then we perform the state readout, and then we look for correlations of the ions. And we do this, of course, over and over, repeated every 100 milliseconds. In this case, the experiment actually every 120 milliseconds. And as the Earth rotates. And if there's Lorentz violation, we should see actually that there's an energy modulation with a period of 12 hours. So we look for these energy variations. So here you can see the gray data point as an estimate of the frequency. These points are pretty Gaussian distributed. So we think them every hour. We basically calculate the mean and an error on the mean. And then we try to fit the sinusoidal to this curve with a certain amplitude, but a 12-hour period. And what we find is that our error is compatible with 0. The error on the amplitude is compatible with 0, and we have a statistical uncertainty of 11. What does it mean? We found this 12-hour modulation to 11 millihertz. We have to compare this 11 millihertz, which corresponds to 5 times 10 minus 17 electron volt energy, to the kinetic energy of the electrons themselves, which has been calculated to be about 50 dB. And that basically gives us a sensitivity on the order of 10 to the minus 8. What is interesting from a technical aspect is how this bound varies as a function of the averaging time. So if I take only small chunks of the data and look how accurately I am, this is plotted here, and what you can see is the longer we measure, the more accurate. This is by no means normal. This is only very rare exception. This happens because if you have systematic errors, you can actually typically what happens when this is called the so-called Allen deviation. It goes down and then it starts to go up as, for instance, temperature trends. So this works nicely, and they just about a factor of 2 higher than what you would expect from actually quantum. But the interesting thing is, and yeah, it also averages down really with the square of the time. So it seems that we have a very good grasp on systematics, and that we just would need to measure much longer to actually get more precise. So what does it mean in a context? Many people have measured or tried to look at Lorentz violations of electrons. So here are experiments coming from optical resonator experiments. We'll see in a moment actually how this actually would be possible to do. Mike Borsey and Dimitri Butcher collaborated on measuring in dysprosium certain energy levels as a function of also the direction of the magnetic field, the Earth rotation. And that was the most precise test up to 2013, and our work improves by about 2 orders of magnitude on this end. And because it worked so well, we looked a little bit more into what it means. And that's what I really finally point there. It's the interpretation. And when you interpret these results, you really have to realize that you need to pick a reference frame. You cannot measure a physical quantity without comparing it to something else. So you need to carefully think about what are you comparing. So it could be, for instance, that the electron doesn't obey Lorentz invariance, so that's why I put it to speed, right? So if that's the case, so what I assume here is that the Coulomb potential is really symmetric. But if I see a signal, so I might say, oh yes, the electron doesn't obey Lorentz invariance. However, nobody tells me that the Coulomb potential needs to be symmetric, especially if I consider weird things like that the speed of light is maybe not isotropic. Then it's natural to expect that the Coulomb potential is symmetric, right? The photon covers presumably the Coulomb force, so if the photon doesn't have a proper dispersion relation, there should be also the Coulomb force shouldn't be symmetric. In this case, if I see a signal, I could say, hey, wait a moment. My Coulomb potential is not symmetric, the electron is perfectly fine. So what we're actually doing here is we probe the difference between the electron and the photon dispersion. That's what we're doing. I want to come back to the original Michelson Morley experiment and point out some things here. The same holds true for the Michelson Morley experiment. To analyze the experiment, we need to pick a reference. So either it could be that if I see a signal that the photon travels in this direction faster, or, and I don't know that, the arm got short. If I look carefully, what determines the arm length is a macroscopic body, it's a crystal. There's Coulomb interaction in the crystal, and also electrons moving there. So together, the Coulomb force and the electron dispersion govern the length of this arm. So this experiment measures also the difference in some respect between the speed of light and the electron dispersion. You might even claim that this is worse because I measured the difference between photon dispersion relation and if I pick the wrong crystal, mainly the Coulomb force. Well, if that's not 0, then probably something is really serious. So what we can say is that both experiments compare with a different linear combination, but they compare the photon and the electron dispersion relations. So it's valid to put our point on this graph of the original Michelson Morley experiments. We are down here at 10 to the minus 18, including on the best S of Michelson Morley. So with this, I want to summarize. So we work on novel quantum information processing architectures, especially we are interested in combining solid-state quantum information processing techniques with ions. I showed you how we can improve ion traps. We also work on quantum many-body physics, studying quantum correlations, or we studied energy correlations, energy dynamics already in the system. We are now at the point where we're looking at quantum correlations, hopefully very soon. And the 2 points I talked about is how we prepared an ion trap first time, a scalable ion trap first time compatible with fault-tolerant quantum computing. So we haven't done fault-tolerant quantum computing for sure, but it's now at least compatible with it. It wasn't the case before, and we verified that Lorentz symmetry holds at a level of 10 to the minus 18 for the difference between electrons and photons. I want to thank, of course, all the people who did the work. Ishan and Nikos, they're doing mainly the work on together with Sebastian, who is not on this photograph, on the ion, cleaning the ion trap and understanding the surface noise. And Crystal, Noel, and Maya joined this project recently. I had 2 really excellent graduate students doing, amongst many other things, this Lorentz invariance test, Hong and Michael. Hong moved to Wickham, and Michael is wanted to stay in the area. He went to industry. He had also fantastic support from Michael Bodensee from the Willer Group of understanding what we are actually doing, because we are complete newcomers to this business of testing Lorentz. And the group has recently changed a lot. So I want to acknowledge that we have many visitors, and at the moment, 5 graduate students and 3 postdocs, and also some fantastic undergraduate students really doing some interesting projects. And finally, I want to thank you for your attention. So what happens if you do this cleaning? Half of the time the ion gets short. So we need to work a little bit on improving how to remain the shorting. And then our ion traps, basically what we need to integrate it all at the same time. And they are constraints with optical axis. The problem is on this arm, we need to rotate it, and it's kind of shaky, and that's not good for coherence. So what we need to come up with the geometry, how we can implement, have this ion gun there without obstructing our optical axis, for instance. And then what I didn't talk about is whole quantum computing business. This is a multi-parameter optimization process. So everybody tries to optimize as much as possible. Then if you introduce one more thing, things explode and we might do things different. Yeah, so that's basically what, and it's a major technical challenge. So if you look at, there are 2 labs who are really doing quantum computing. That's Dave Weinert at NIST, and that's Rainer Blatt in Innsbruck. If you look at their groups, they're completely differently structured. So there's a huge amount of technological work. If you have them, you can actually have the precise laser control here also. This is but what basically collaborating with Rainer Blatt, and the idea is now to transfer that knowledge to Innsbruck so that they can make use of it and improve their quantum.
Okay. So for much more to your equipment, so you have to limit. What is the limit? It's a matter of integrating with time?
Yes, it's a matter of.
You can actually increase that value at that.
Yes, yes. So 100, I think you can do. So it's at this point we believe it's a matter of time, but that's very deceptive. So we measure for 1 day. If you measure for a year, it's very and beyond a year it doesn't. get practical. So that's kind of so we need to work, and that's basically have some ideas how we can speed up the process, and I believe we can get a factor of 100. And then what we run into is black body radiation being maybe non-isotropic. So I looked at it, and it could be that black body radiation is not isotropic, and for those of you who know what the AC Stark shift is, black body radiation can create an AC Stark shift, and if that AC Stark shift is not isotropic, and the temperature is not constant either, and temperature most likely will have a 24-hour cycle, and then you start to be sensitive to that. But other than that, I cannot see. So we're going to give it a try and get another word. But I think then this speeches.
Did Michelson Morley look for a 6-month periodicity too? And could you do that as well?
We could do that. That's actually one thing which we definitely want to do too. And that basically would test, so the Earth revolves around the sun, and it changes its speed through a hypothetical background field, for instance, defined by the cosmic background. And this way you can test. So I didn't talk about this. There's a whole theoretical framework which is called the standard model extension, and we could test other coefficients in this model. Yeah, so that is definitely something to look at. And what will be interesting will be to see whether we have systematics on the time scale of half a year, right? Having no systematics on the time scale of a day is one thing, but having no systematics change over 6 months, who knows what's coming up. And so that's something. What I'm really curious to see when we repeat the experiment, what we will find then, whether we find the same values or something else.
Tell me what pressure you use on the Michelson Morley experiment.
That was 10 to the minus 11, 10 to the minus 11 millibar.
It looks like it's quiet. Other night before, less than that, it's got a vibration. There, interaction, like you say, what is in this interaction?
The problem is if we increase our pressure, the ions, they're very reactive. Like you took one electron away and they really would like to have that electron back. So, yeah, so I mean, I cannot imagine. I mean, the gravitational forces are so much weaker than the electromagnetic forces. I cannot imagine the gravitational forces.
Can you show us the graph of the whole versus distance of the plates? You had higher fault tolerance. It seemed that there was already more like
If you're closer, yes. So that's counterintuitive. So the reason is because you can go slower, not faster. If you go closer, your quantum gates get faster, roughly by the distance. And that's why you can tolerate more noise. What was plotted there is not the error rate, it was the noise. So if you can go twice as fast, you can tolerate twice as much noise to get the same error rate. So that's why this is.
Okay, one last question. Okay, let's